right, so if you didn't get your exam, just swing by office hours today and I'll give them to you, or anytime this week or next week even if you want. So now let's go to the document camera. And we're going to start on chapter 23 right here, looking at we're looking at regression lines, and we're going to look at the errors around the regression line, and then we're going to do inference for regression, just like we did for means. But now we're going to do it for the regression line. Okay, so the standard deviation of the prediction errors, also known as the root mean square error. So when we do these regression estimates here, we have this regression line here, and that's our prediction line. We make predictions for y. We're predicting y from x, and this is our best prediction line right here, but we have scatter around it. So the prediction error, also known as the residual, you'll see that word a lot, is the actual value minus the predicted. All right? So for example, is this looking clear to you, or is this, everything looks blurry to me, so I can't tell. But is that clear to you guys? Is it doesn't look like it's very focused, right? All right, so I'll try to make it better. Yeah, that's better, right? Okay, so you see, like, for example, these points, A, B, and C, are off this regression line. So sometimes it's easier to look at, so this distance here between the actual, this is the actual final, this is finals being predicted by exams, the actual final score of this person of point A, and that's the actual, and the predicted is down here. So this is the predicted right here. So this right here, this distance is the error, the prediction error, or the residual. And it can either be positive if they're above, actual minus the predicted, so this would be positive, or negative. All right? So what are the residuals of the following points? How far above or below the regression line are they? It's kind of hard to see here because you'd have to read off this distance versus that distance. So what often is done is you'd plot x, or sometimes even y, against the residuals, on this axis. Okay? So you'll often see that, and so this point A is easier read here because this is 0 right here. It's above or below the line. And by the way, the average of all the residuals is 0 right here. So this is the average of all the prediction errors. That's 0. So I think you could, let's do an iClicker here, and I'll give you options. Let's do that. So get your iClickers out. So here's your options. And so which one of these points here do you think has residual -7? Point A, point B, or point C? Did everybody get a chance to vote here? Okay. I see some people. All right, so let's stop it and see what you said. Great, it is point C. So let's go over to the document camera again. And you You see, point C is, you know it's negative. This is negative, and it looks like it's about -7 here. Your choices were -7. This has a big negative residual. It's really far below. So this is -22. And this one is the only positive one, which I gave you the option of 17. So those are the residuals there. Now, instead of actually, so for any regression line, the average of the errors is always 0. It's always 0. That's actually an exam, a homework question on your homework that's due, I think, it's due tonight, I guess. But what's the typical size of these errors? We want a way to say, okay, how, our regression line is, what our best prediction, but we want to put some wiggle room around our predictions because, it's unlikely that the point is exactly on the line. So plus or minus about what? Well, if we just took the average of all the residuals, we'd get 0. We could take the average distance, the average of the absolute values, but we don't do that. And you've seen over and over again that it's more useful to do what? To take the standard deviation as the average deviation squared from this line, the standard deviation, instead of, we've done this over and over again. So the standard deviation of all these distances, all these points, how would we figure that out? The standard deviation of the errors is also called the root mean square of the errors. You know why? Because what are we doing? We're taking all the errors, which would be for each little point, x sub I, we'd subtract off, or y sub I, because they're y's right here. So for each point, we'd subtract the actual or the observed minus its predicted. So that would be y sub I, and we're going to put a little hat over it for predicting. These are all these distances. They can either be positive or negative. But if we just took the average of those and summed them up, right? So we'd have the sum from I equals 1 to however many points we have. If we did that, we'd get 0. So instead, we could take the absolute value of this difference, and sometimes that's done like that, but the absolute value, but instead we square them. And then this is called the variance, and then the square root is the root of the mean of the squared errors. So that's called the root mean square error, or the standard, same as the standard deviation of the errors. Those two things are the same. Okay? So this is just it's the way we always take a standard deviation. All right. So, and it's a measure of the typical spread around the regression line. Okay. And we've got this really nice formula for it, because can you imagine for all these points, there's like 100 points here, having to do this? Instead, there's a really nice formula, right, that we're going to be using right here and at the bottom of your page. And what it says is that the standard deviation of the errors, it's related to the correlation coefficient. And it's related to the spread of the y values. Okay, those two things. Now, let's think about it. If our regression estimate is perfect, let's look at this formula, when r is equal to plus or minus 1, what do you think this is going to look like? Well, if you put plus or minus 1 in here, what do you get? The standard deviation of the errors would be equal to the square root of 1 minus plus or minus 1 squared, right, times the standard deviation of the y's. So that would be what? 0. So the standard deviation of the errors would equal 0. And what would the plot look like? That makes complete sense, because when r is equal to 1, plus or minus 1, let's just do plus 1. If it was plus 1, the points would all be on a line. And we'd have no residuals, no error. So that makes total sense if it was negative or positive. So it makes sense then, and that's what I say here. How about when r is equal to 0? Let's try that. So when r is equal to 0, then the standard deviation of the errors is equal to the square root of 1 minus 0 squared times what? Times the standard deviation of y. And that would be that's the square root of 1 minus 0 squared. So that's the square root of 1, so it would just be the standard deviation of y. Does that make sense? It's a little bit harder to see, but think about it. I'll do the picture right up here. When r is equal to 0, what does that mean? It means that knowing x tells you nothing about y. I'll just do it in this positive quadrant. Right? It would have a scatter plot like that. Knowing what x is tells you nothing about y. So no matter how low or how high x is, my best estimate for y would just be the average of all the y's. And r is equal to 0. It's a completely flat line. And no matter what, knowing your height tells me nothing. Let's say this was height in your exam score. Tells me nothing about your exams. So no matter how tall you were, my best estimate for your finals, for your exam, would just be the average of the exam scores. Because why would I guess higher or lower? I wouldn't. So it would look like that. And then the typical spread around here, the typical spread up and down, is just the spread of the y values. If you all scored at the average, there'd be no spread. It's just how spread out they are here. I think our exam scores were, I can't really remember, probably about 10 points. So does that make sense? And that's why when r is equal to 0, our best estimate, our best prediction is just the average, and the spread around the average is the standard deviation of y. So that's the idea. And any questions so far? Okay, and by the way, we'll give you this. This will be given on exam 2. I'll give you this. Okay, so now let's go to our next page here. And this r, and particularly the square of r, is going to come up a whole lot in multiple regression. It's called the coefficient of determination. I don't know if you've seen that term before, but what it is the fraction of the variance in the y values that's predicted by the regression line. So you can see that by squaring both sides. So if you square the standard deviation of the errors and you square this side, you'll get the variance of the errors, which is equal to 1 minus r squared times the variance of y, if you just square both sides. So 1 minus r squared is the proportion or the fraction of the variance of the y that's in the errors, which means that r squared must be the fraction of the variance of the y that's predicted by the regression line. So why I'm talking about this now is because r squared, right, is a capital R squared, this is a special case of this, when you just have simple regression, 1x predicting 1y. Soon we're going to move on to multiple x's predicting 1y, like exam 1 scores and homework predicting your exam 2. And then we use a capital R. I'll explain that later. But it's a key statistic in something called ANOVA, or analysis of variance, which is what we're going to be doing. This course really is a lot about linear models and looking at analyzing linear models, getting the confidence intervals for the predictor, for the slopes, and looking if they're significant and doing all our significance tests, we're going to use something called analysis of variance. And that's coming up. And this is a key statistic, so I wanted to show it to you now, this R squared. Okay? So, now, so here is this scatter plot, which is what we had before. And here's the regression line. Right here, this is the regression line. We're predicting exams on the x-axis. And here's finals on the y. I should pull this data set up for you. It's called the grades. It's in our data set. We'll look at it later in a few minutes. So this right here is the regression line. And do you see this line here? Remember the steeper line? That is the standard deviation line. And right here, this point is what? That's the point of averages. That's where they cross. Okay, so it's that point right there. It's what? It's 83, 73.6. That's where the two lines cross when z equals 0. All right, so we have, this is x, and this is y. Y is always what you're predicting here. Well, that's why I put finals. It makes more sense to, exams come first. Makes more sense to use them to predict the final. Okay, so now we want to find the equation of this regression line, right? So we want to find the regression equation. So it will be finals equals, we're going to put the intercept first. We always do that. That's like B naught plus B1 times the exams. So this is final and this is exam. And we want to just find the intercept and the slope. We'll find the slope first, right? And remember how you do that. The slope, we had this last time. And this is, you won't be given, so please remember this. It's R, and you've given R right there, 0.6, times the ratio of the standard deviation y over the standard deviation of x, rise over run. So in this case, it's 0.6, and now we have to look at the ratio. This is where you have to keep them straight. Okay, it's standard deviation of y over the standard deviation of x. And they won't always be in a table with x on top of y. I remember I did that on the students saw this so many times that they just assumed the top one is x. I don't even really pay attention to that when I'm making up exams. So make sure you know whatever you're predicting is the y one, right? Okay, so that's 10.3 over 9.2. And rounded, I got 0.67. So that's what we're going to put right in here. That's the slope. Now to get the intercept, and I'll tell you, the intercept is not usually very important. People don't really care about the intercept much. We're going to be building confidence intervals around the slope, and we're pretty much going to be ignoring this intercept. But to get it, you should know how to get the intercept. And remember, if I plug in any xy point for these, I can solve for it. And I know the point of averages, so I might as well use that. So I'll use 73.6. I'll plug that in for the final, is equal to this intercept plus 0.67 times the average for the exams here, which is 83. And I solved that, and I got this is equal to, I got 17.99. Why don't we round it to 18? So that's going to go right in there. So that's our regression equation right here. That's our equation. And then we're going to use this, just if I gave you an exam score, you could predict what they'd get on the final, which is just finding the y value here. on this line. So let's do that for somebody who got a 90. So we'll just plug in 90 for the exam. And we could look here, 90 is about right here, and we could estimate it's like over here somewhere, like below 80 somewhere here. Okay? Or we could do it by, or we could do it by the 3-step process too. But let's do it by using this. So all we say is, okay, the predicted final, I'll put a little hat over it, the predicted final here is equal to what? 18 plus 0.67 times 90. And I got 78.3. Okay? So that's the predicted. What did the person actually get? The person was actually above that. That's what oh no, we don't know what the person got. Do we? We don't. Here, I tell you down here, suppose the student really got an 85. I'm jumping ahead. I didn't tell you. All we know is the prediction. For everybody who got a 90, right here, this is our best prediction, but there's scatter. Okay? So do you think the prediction will be exactly correct? No, not exactly. So we need to add some wiggle room. So this is our point estimate. That's our point estimate, but we want to put a little bit of margin of error around it. So that's what we're going to do. So we're going to attach some wiggle room to this estimate, all right? So we're going to say the prediction plus or minus some, I'll just say, what's the root mean square error? Let's do that. So in this case, so for this, it would be 70, our prediction right here, that's our prediction. And if we want to give a range to it, like I wouldn't, like you'd be interested if you asked me, you got, a 90 on the first exam, and you wanted me to predict what you'd get on the second exam. If you were in this group right here, or a similar group like this, I would say, let's say everybody had taken the exam but you, and you just wanted to know how people were doing. So I could say, I'd say you'd get a 78.3, give or take some leeway. Well, if I said give or take 1 point, that would be a lot different than if I said give or take 10 points. So you want to put a range to it. You might be wondering why it's so low if they got a 90 on the first. Well, look at these. The average for the final was pretty low. They still did above it, the prediction's above average. All right, so we have to add some wiggle room to that. So we have to compute this root mean square error for it. So how do we do that? So we have to, the root mean square error is equal to what? You probably don't remember it. It's the square root of 1 minus r squared times the standard deviation of the y's. So that's going to be the square root of 1 minus 0.6 squared times 10.3. And it's going to be less than 10.3. This number is always going to be between, look at it, it's going to go between 0 and 1, and it reduces it to 8.24 from 10.3. So if I wanted to add that here, I'd say, okay, so the prediction is 78.3, just plus or minus 8.24. Any questions so far? So you could give it a range. You could add and subtract that, and you'd get what? 70.06 all the way up to 86.54. So it's giving it a range. Sorry, that's hard to read. I just added and subtracted 8.24. So that's 86.54 up there. All right, now suppose the student really got an 85. What's the student's residual? All right, so the student's residual, or its prediction error, is always equal to the actual minus the predicted. And there's the actual right there. So that's equal to 85, and the predicted is right there, 78.3. So it's what? Let's make it 75. I just want to show you why it's negative sometimes. Let's just do 75. Let's say actually got a 75. So you'd see that put the actual first minus the predicted, and now you get a negative number, so it shows you it's below what's predicted, and it's negative 3.3. Okay? That tells you, the negative tells you it's below. So make sure to actual minus predicted. Any questions on that? All right. So let's move on. And now we're going to use this normal curve again in cases where the scatter plot is roughly elliptical shaped. We can use these the normal distribution for any vertical strip. So what I mean is, like for the people, we just looked at the people who scored around 90. So within this vertical strip here, if I could draw it in 3D, what I want to show you is that most of the points, like 68% of the points, are going to be within, here's your regression line right here, and here's one root mean square error above, so that's plus 1 standard deviation of the errors, and this is going to be minus 1 standard deviation of the errors. And this right here is the regression line. And then what's this one and this one? This is plus 2 standard deviations and minus 2 standard deviations of these errors. So if you can imagine, like for all the people who scored a 90, it would be they'd be bunched around here, and it would resemble a normal curve. So the points within 1 standard deviation above and below, about 68% of the points would be in here, and about 95% would be contained in there. But I can't really draw it above, so I'm just going to make it like kind of look that way, like that. Okay? And that's true all across. It's true everywhere, through every vertical strip. It would look about like that. And so between here and here, that's 68% of the data lies, and between here and here, that's 95%. Maybe it's easier to draw it here. So between here and here, this right here is 68%, 68% in that range, and then here is 95%. You know what? I think I should show you the same data so you can see it on the here. So let me just show it to you. And so if we go to our data program, we can pull up this data set that I'm looking at, and I encourage you to do this. It's called the grades. It's from a while ago. In these are grades from Stat 100 when I first started teaching, actually. There weren't very many people in the class, and there was 107 in this class. And so if you look at the scatter plot, and you plot the exam average versus the final, you'll see what we're looking at. And you can look at the regression line here, and there's the standard deviation line. You can also look at the residual plots here. That's what they look like. That's what we did, and we looked at some of these points here. I think we looked at this one, and that one. Let's get rid of that. And now what I want to show you is if you go, okay, so this is the regression line. If you go one root mean square error above and below, 1 standard deviation of the errors. Can you see this yellow line? That's about 68% of the data. And if you go 2 standard deviations, that's about 95% of it. It's a pretty nice, it doesn't really look elliptical shaped down here. There just aren't very many points down there. So that's the idea. And the regression line, well, first of all, here's the statistics. I used rounded statistics. So we're not going to get exactly the same regression line that we got. But if you look down here, we got the final is equal to 18 plus 0.67 times the exams. And R is about 0.6. And we got standard deviations of the errors of about, what did we get, 8.24? So we used rounded statistics, but that's where it's coming from here. So any questions on that? All right, so let's go back to the document camera. And now what are we going to be doing here? Okay, so we're going to use this to look at, okay, so looking at the scatter plots above, it looks like we can apply the standard deviation rule of thumb. So let's do it. So we can, about 68% of the time, our predictions of the final based on exams will be right to within what? So 68%, that's a Z star equal 1. So it's going to be right. So we're going to look at our prediction. Plus or minus, it's going to be 1 root mean square error, or 1 standard. I'm using the standard deviation of the errors and root mean square error interchangeably. So remember, our prediction is 78.3 plus or minus, I'm just saying for this person here, where's the 78.3 coming from? I'm just looking at this one strip here for people who got a 90. Okay, so you make a prediction, that's your point estimate, and then you want to put some margin of error around here. So I'm going to say about 68% of the people who scored 90, this is just for scoring 90, 68% of them will be 78.3 plus or minus 1 times 8.24. And about 95% of them, I'm going to use Z star equals 2, or 1.96 here, will be right to within how many points? So then you just say the prediction plus or minus 2 root mean square errors. So this is all for people who scored 90. Plus, but you do the same for anything. You'd make some prediction, plus or minus 95% would be within 2 of our root mean square errors. That's 8.24. Okay? So that would be within 16.48 points. All right, if we wanted to do 82% of the time, well, I don't know that one offhand, so I'd have to, look at the table and figure out what the Z star is here, what the critical value for Z is at 82%. So I just look in the back here. And 82, middle area of 82. This is where this type of table comes in very convenient for confidence intervals. So this is 82 is about right here. So 1.35 I'll use. So then I just say 78.3 plus or minus 1.35 times 8.24. And I got this. Okay, so that's basically, these are you make a prediction and you're putting some wiggle room around it, and you can say what percentage of the points lie within that in that margin of error. But that's only if you have a pretty nicely shaped football-shaped cloud here. If you don't, you can still make these predictions, you can still attach margins of error, but you can't do this 1, 2, 3 rule here. You can't apply a normal approximation here if they don't have a sort of nice shape like that where most points are hugging the line. So speaking of that, we're going to look at how to make not only, like right now we attach margins of error to our predictions, but now we're going to look at attaching margin of errors to our slopes. Like imagine that these 107 students weren't the whole class. Let's say they were randomly sampled from a much larger population. Well, then each time we took a sample, we'd get a different regression line. So what we're doing now is we're going to look at confidence intervals and significance tests for the slopes. Just like we did before for our means, now we're going to just do it for slopes. So we're going to use a lot of the same methods, so everything's going to look very familiar. So let's get started with that. So any questions before we look at this inference for regression? You did not do this in AP Stats? I don't know. Anybody who took AP Stats, did you put error bars around your slopes? Did you look at that? Did you do multiple regression and do significance tests like T or F tests for slopes? Okay, so that's what we're going to be doing, a lot of that from the rest. It's going to be a lot of this rest of the course. Okay, so let's start. We're going to start understanding it with just a simple regression. When I say simple regression, that means just one X. Just we're in 2 dimensions, just one X predicting one Y. Okay, so now the idea is this. If we randomly sampled our data from a larger population and we want to make an inference about the regression line for the larger population, we're going to get a sample regression equation, and we're going to use that, the sample, to estimate, to make inference about the population regression equation. And then we're going to compute standard errors, confidence intervals, and perform hypothesis tests. So that's what we'll be doing this week for simple regression. Okay, but before we start, we have some assumptions to make about applying this regression line to a wider population. Okay? So we have these 4 assumptions that we need to make. And the first is linearity. Well, we use that even if we weren't doing inference. We don't want to fit a line to a curve. So that's the same assumption. To use regression line at all, it doesn't make sense if you have a curve. So that's the same one we know. But then we have these other 3 assumptions about the errors around the regression line, that they're independent from each other, that they have equal variability across the line, and that they're normally distributed. We just saw that that they're normally distributed. So let's look at these 3 assumptions. So just as usual, just to get started, since we're talking about a sample regression equation in a population, we have to distinguish them. So we should use Greek letters for the whole population, the ideal, beautiful population out there that we don't see. And then we have the sample that has a lot of error in it, and we use Roman letters for that. So we're going to do the same thing. So here's our Greek letters for the intercept and the slope, and we're numbering them because here's the intercept. That's like when you have 0 slopes. This is the first slope for x1. And then we're going to add, like this, right now we're doing finals is an intercept being predicted by exams, but we might want to add homework average. We might want to add a binary variable. We're going to do that, a categorical variable like gender. We're going to add a lot of different variables to make a better model. Okay? But we're starting with just one, and here's errors, because this is the regression equation, because it has where the errors, and they're assumed to be independent, normally distributed with equal variance. Okay, and here is our sample regression equation, and we're putting a little hat over it. I could either add error or put a little hat here. When I put a little hat, it's the actual prediction, plus, and here's my Roman letters. All right? Sometimes people put hats over these too. All right, where y hat is a predicted value of y. So let's just do our same example just keep on that same example that we did on page 113 here. Let's just use this same example. And this had 107 students. I think I'm going to pretend I just sampled 100. I'll use these same statistics here. But pretend, suppose the exam averages, this will just change n slightly, just to make our calculations a little easier. So this is n equals 100 students from the previous example, were a random sample from a much larger class of Stat 100 students. Let's say there were 2,000 in the big population. How could we use that sample slope that we got in our regression equation, the sample 0.67, to predict finals from exams to estimate the population slope? Okay, so here's our sample statistics, right? And now, how are we going to get, first, what are we doing here? Let's set up a probability, a box model, because now we're making inference. So what did we do here? Imagine that we had some population scatter plot. So we had some population scatter plot. This is what we're imagining of, okay, so here we're having the same thing where we have exams and finals. And it's going to have how many points in it? It will have 2,000 points, right? One for each Stat 100 student. So it's going to have 2,000. I'm not going to draw them all. It has tons and tons and tons and tons of points. Now, we don't see this. This isn't what we don't really know this. We don't know this. All we see is this, pretend these were randomly selected. So we pretend we just randomly chose 100 points. So we randomly 100 students out of here, okay, without replacement. And then we get from all 2,000 students in the population, okay? So then in our sample, these are our sample stats, okay? And then we get the sample stats above, okay? And we got a sample slope. We just did it before. We got a sample slope, and it was equal to r times SDY over SDX. We just did that on the previous page, and we got 0.67. That's what our slope was, and we got this regression line. All right, now we have to look at our regression plot, and the first thing we want to do is, does the plot look like it may well fit with the straight line plus scatter? Remember we had it, so you look on the previous page, did it? Yes, it looked pretty good. I'll draw it again. So we want to check for linearity first. This you should do even before you get that regression equation. Just check and look. And we did, and there we, in our sample, this isn't our sample, we're checking. And here's your exams, and here's your final. Now we're just checking the 100 points. And it looked pretty good. It looked kind of like that. It looked like we could fit a nice line through it. So this is good, as opposed to what? And then we did this. So we got y equals 18 plus 0.67x. And that looked pretty good. That's what this is. So, but what if we'd gotten something bad? Like check for linearity. So this is good, but something bad would be like what? It would be a curve. So if we had something, or just not, it might be something like, something like clearly could be, you see a lot of these sort of J-shaped curves, it might be something like that. Clearly you can do better than a line. You don't want to fit a line. So this would be, if you fit a line, that would be bad. Or it could be, I don't know, anything. something like that. It could just be whatever. But you don't want, these have curves and you wouldn't want to do, it would violate linearity and you wouldn't go any further. Okay? And this is bad. Well, that's the same for with our sample even. We wouldn't fit a line to something that followed a curve like that. We'd want to do a curve. Okay, so these show curvature, and so we don't want that. So we'd do better fitting a curve or transforming the data. And we'll look at that later at the end of the semester, towards the end. What do you do when you have that? Okay, but now let's just assume we got the line. It looks good, and now let's think about the rest of our assumptions. So we're on the next page. And, if you go on in statistics, a huge amount is checking these assumptions. When you do applied statistics, a lot of the courses you check all these assumptions. I actually find it really boring to check these assumptions because they're always violated somewhat, and then it's just a judgment call. But I just want to give you the basic ideas. All right. Now, so you know that our sample slope clearly is that's what we're going to use to estimate our whole population, but it's going to vary. Why? Because every single time you took another 100 points, you're going to get a different regression equation. You're going to get a different set of 100 points, a different sample, and you'll get a new slope. And you'll do that, so it's going to vary. So we want a way to describe how much it varies. This is different than the standard deviation of the errors. That's how much our prediction varies. We're talking about how much our slope changes each time we take a new sample. All right? So we're going to describe that with a standard error formula. How much the slope typically varies is called the standard error of the slope, the sampling error of the slope. And it follows its own square root law. You're going to divide by the square root of n, like we always do. Remember how we always take some standard deviation divided by the square root of n, or multiplied. But in this case, it's going to be divided. It's more like we want the average here, the average. It's like a standard error of the average. So it looks great, except for this right here. Why do we have that? Well, the formula makes sense. The variability of the slope comes from the random error of y's around the prediction line. So the bigger spread that you have around your prediction line, the more they're spread out, the more your slope's going to vary, right? But, so let's look at this. So this is the standard deviation of the errors, remember, is the square root of 1 minus r squared times the standard deviation of y. All right? So why don't we just stop there? That would make perfect sense, right? Because the standard error of the average, for example, is SD over square root of n. So why do we have that? Now it's really easy to remember. Well, think about it. You're going to say, okay, the slope, which is rise over run, right, y over x, is going to be something, give or take a certain amount. So you would be in the wrong units here. The variability is described in terms of y, and slope is change in y per unit of x. So we have to divide by this just to get the units right. So that's where that comes. Okay? SDY over SDX. It's going to be the slope is something, so many, you're going to, for each extra point on your exam, you're going to go up or, the slope tells you how much you'd go up in final points, but final points per exam point. So SDY over SDX. So that's the idea. And it makes a lot of sense. As the bigger your spread around the line, the bigger the SD of the errors is, the more your slope's going to bounce around. The bigger sampling, standard error you have for the slope. But what about n? The bigger n is, this is your sample size. the bigger your sample size, the less your slope's going to bounce around. And it's going to be less by it's the square root law, by a factor of square root of n. This makes total sense. Like, let's just think about it. Let's say instead of we took 100 points out of here, so we got, we get a better, more stability if you took another 100 points over and over again. Then what if you just took 3 points? You could get anything. You could get like 3 random points. Let's say you took this one and that one. You could get a very high slope. But you might randomly get this, this, and this, and then it would be a negative slope. It's going to bounce, your slope's going to bounce around a huge amount if you only have a few points. The more points you have, the closer your slope will be, the less error you'll have, sampling error. The more it will resemble your population slope. There's some true population slope here, we just don't know it. This is the true population, and we get, each time we take a sample, we're going to get, if we take a big sample, you'll get close to that. If you just take a few points, you won't. So that's the idea. So now you understand this, but this is going to be given to you as well. But it's really important to get formulas you understand, I think, that help you learn it. Okay, so now we need these two assumptions to do what? To calculate the standard error, the slope. So let's look at these. So independence. So the next two we're going to look at, we need them for the standard error of the slope. All right, so independence, what does that mean? It means that when you're sampling, that these errors here, these errors are not dependent on each other. So like, remember, you're randomly taking them. So if you choose like 1n, that doesn't mean the next one is somehow determined. It's going to be like closer to the line. This has let's say you chose that point. Maybe if they were dependent, maybe there'd be a bunch that were just clustered there. So you'd have a chance of knowing one of them, they'd be correlated with each other. So you really wouldn't you wouldn't have as big a sample size. You'd have correlated errors. You need those standard error formulas depend on independent draws. You draw one, theoretically you're supposed to put it back in here and it's not going to have any bearing on the next one. But if you have dependent draws, somehow if you get a big error, it'd be linked. Maybe it would give you a big error down here. Maybe if it was dependent, it said, okay, it'll be linked with an error up there or something. You don't want that. You want independent errors. Otherwise, our standard error formulas don't work. Okay, so how do we check that? So basically it's asking, can we model our data as random draws from a larger population or as random assignment to experimental condition? And how do you check it? You should show no grouping. Check that you have no grouping or pattern. This matters because if the points aren't independent, like let's say you have lots of identical twins, then in effect we don't have as big a sample because you're really getting two of the same. Okay, so here's the idea. So this would look good. We've already seen that looks good. There's no grouping, so that would be good. And something like, you could have linearity, but maybe have like a whole cluster of people here, and then a whole cluster of people there, and then sort of random scatter. Something like that. And maybe another cluster of people here. That would be bad. You don't want something like that. All right, now equal variability. Okay, what's that? So, here, all these, I'm giving you the ideal plot here. Equal variability across X. When wouldn't you have that? Something that often comes up in our data is these fan-shaped things, like they look like this, where you don't have very much variability. Then when it gets higher as X, something like this is terrible. So this is bad. A fan-shaped plot. We have a lot of these in our data set, and we're going to look at how to deal with it. But why is it bad? Okay, the spread should be about the same across the plot. This is called equal variance. You probably seen it as homo. Equal is homoscedasticity, like homosexual. Same sex, same variance. Homoscedasticity, that's good. Heteroscedasticity means unequal variance, and that's bad. You might have seen that term, or you will see it. Anyway, okay, so why? This is needed because how much the scatter affects the slope depends on where along X it occurs. Look, if you change Y or have an outlier near the middle of the data set, it doesn't tilt the slope either way, but changing it at the extremes is going to, like way out here, will pull it up and down. So if you're doing these random samples and they're way up or way down here, you're not going to have the same variability as that standard error formula gives you. We're going to apply this. This has to be applied across all the X's. So that's bad. All right. Now, you can look at the residual plots. They're usually easier to look at. And now we're going to attach. Okay, so now what do we want to do? We want to give our, first of all, we have to compute the standard error for the slope. So what is the standard error for the slope? If we check all those assumptions, we can compute the standard error for the slope. So let's do that. So the standard error of the slope is, and we'll just do it, the square root of 1 minus r squared over the square root of n times s dy over s dx. So when I did that, I got the square root of 1 minus 0.6 squared over the square root of 100 times 10.3 over 9.2. All right? So we're just going to give it a range. So a range would be what? A range would equal our sample slope plus or minus just the standard error. So it would be 0.67 plus or minus that. And when I did this, I got 0.09. See, it's not very big. That's the idea. Okay? And now we're going to use that to build confidence intervals, finally. Okay, sorry it took so long. So let's just do this part, because you've already seen this, so this part should be pretty easy. So we're going to use confidence intervals using z star and the normal curve first on this page, just to show you what we're doing, and then we're going to use it on using t star. Okay, and the confidence interval is going to have the same form as what? We've done this before, is usually with our sample statistic. Now our statistic is the slope, so it's the sample slope plus or minus z star gotten from this normal curve times the standard error for the slope. And okay? So in our example, let's just continue with the same example. It's going to have this form right here. So our confidence interval right here is going to, before we forget what our numbers are, this was what we computed to be our sample slope. And then plus or minus some z star times the standard error for the slope, and we just computed that to be what? 0.09. So that's what we're going to be using, okay? Now these confidence intervals right here, they're just going to be, this right here is, we can use the central limit theorem, because when n is large, the probability histogram for the sample slope follows the normal curve. Since the errors in the slope come from the sum of n independent errors, and the probability distribution of the sum of n draws from a box, right, or the average or the percent, follows the normal curve according to the central limit theorem. So right here we have the sampling distribution of our slope, B1, when n is large. And we'll use the same greater than, let's just, when n, I'll just say is large. Okay? So And here 68% of the time. If we took random samples, n equals 100 from the population of 2,000, each time computed the slope, about 68% of the samples will be within 1 standard error of the true population, and 95% would be within 2. So that's what we're doing. All right, so now let's do these confidence intervals here. Here, suppose we wanted to be 80% sure that the true population slope lies in our confidence interval. How many standard errors do we need to attach? So 80%, what would we do? So we'd have to look at what the critical value is for 80% in the middle. And it's 1.3 and negative 1.3. So I would just do this right here. I'd say an 80% confidence interval for a slope. You take your 0.67 plus and minus 1.3 times 0.09. That's all I'm doing here. And you'd get an interval here. I got the interval, you could do it, 0.553 all the way up to 0.787. And if you wanted to do a 90 and a 95, it's the same thing. So a 90% would be what? It's going to be a little wider. Why? You have the same sample slope, but instead of 1.3, 90% of the curve, the area of the curve is between 1.65 and negative 1.65. So that's our critical value. So now it's a little bit wider. If we make a bigger confidence interval, we can be more sure. And a 95% would be even wider. 2, or we're just using 2, it could be 1.96 to be more accurate. It's the same thing. And we get wider confidence intervals. So this is the narrowest, and this is the widest of these 3, and this is the narrowest of those 3. Now, who can we apply these to? Do we have time for maybe we should use this as an eye clicker? Let's just keep moving. I'll give you one at the end. So, which of the following statements is true? Now, all of these is a 95% confidence interval. So this is, when we did this, this gives you between 0.49 all the way up to 0.85. So we know that these are 95% confidence intervals. So which one of these is true? Well, it can only be applied to the population that we sampled from, which was this. So that's our answer. You can't apply it to a narrower population or a different population. So those are wrong. So now we're going to use the t-distribution for a small sample. So the t-distribution. Now you're going to get wider confidence intervals. When do you use this? When your sample size is small, so the central limit theorem hasn't kicked in. So when these 3 conditions are met, but this is usually the case, small and normally distributed. It doesn't have, okay, so now we have to use, if these 3 conditions are met, then we should use t-distributions. And what we generally do for t-distributions, remember degrees of freedom. So instead of using square root of n, you'd think we'd subtract off 1, but we subtract off 2 here. So this is the big change. And why? Because the degrees of freedom is n minus 2. And you can think about it this way. We're going to look at this a lot, degrees of freedom. Degrees of freedom measure the variability around your model. And if our model was just a point, like the mean, then we had n minus 1 degrees of freedom because we looked at the n minus 1 points around the mean. You have the mean, and then the variation is the degrees of freedom are all the points around that. Now 2 points describe a line, so we have n minus 2 degrees of freedom. To get the idea of how well the points fit a line, which tells you you need at least 3 points. So n minus 2 degrees of freedom. Okay, that's the idea. We're gonna add another slope. We'll have n minus 3 degrees of freedom if we had a plane as our model, because 3 points would describe a plane. Now, you could use, so that's the standard error plus. You can use this for the normal distribution. There's nothing wrong with it. It gives you a slightly better estimate. Just as usual, you can always use this. But when the standard error is estimated from the data and not already known, but when n is small enough for that to matter, the normal distribution also is inappropriate. So once you start using the central limit theorem, people just go ahead and forget about, just use the regular standard error. So there's 2 differences here, and first we're going to do this. We're going to change, and we're going to use the t-curves. Yep, just like we did before. And these are the degrees of freedom. So this right here, k equals 1 degree of freedom, means n equals 3. All right, and just to remind you, the normal is this tall one way down here with the skinny tails. And this one right here, this is the most extreme difference, and look at it. It's much shorter there. So you can see if I want 68% at 1 here, this is for the normal z star. Z equals -1 and z equals star equals 1, right? That's 68%. That's all of this. Now on the t, you're going to go out further to get the 68%, right? You have to go, because it's so short here, so you have to go out further. So the t star, and then I'm doing an exaggerated version. You have to go up, so t star is bigger in absolute than z star, and the confidence intervals using t are wider. All right, so let's do it, and then little time we have left. This is a super exaggerated picture, but you see why it has to be wider. To get 68% using the t, if you wanted to get 68% using the t, since it's shorter, you have to go out further than the 68% using, the z goes all the way up. All right, now maybe I should make it somehow look better. So this could be the z, and then the t, I'll do a different color. I don't know. The t would look like, you'd have to do, it has this part. So to get the same area, you have to go out wider, something like that. All right, now let's just quickly do it now that you know the idea. So we're going to do the same thing, but with the t. All right. So you're going to set up a model, etc., and you're going to have, this is predicting GPA, so that's Y, from how much people drink out of all U of I students. So you have thousands and thousands of points in here. This is all UI students. So all I don't know, thousands of UI students. And we're going to draw from here a small sample, n equals 25. Okay? That's what we're going to get. N equals 25 without replacement to get our sample stats. Okay? And that's right there. That's our sample stats. All right, so calculate the sample slope. So our sample slope is going to be equal to negative. We got this slight negative correlation, which we'd expect negative, but is it going to hold? Is it big enough to hold up in the wider population? Times the ratio of y over x. So that's 0.5 over 5, and that's negative 0.002. That's our slope. Okay, so that's going to be right down here. When we calculate our slope, it's going to be negative. Oops, not 0.02, negative. I put too many zeros in there. 0.02. So that's going to be our sample slope. Plus or minus, now we have to get this t and a new standard error. So, so let's do that. So calculate the standard error plus. Well, the standard, it's going to be the same thing, but instead of having n minus 2, we have, instead of n, it's n minus 2. So it's the square root of 1 minus r is negative 0.2 squared over the square root of 23 times the ratio of the standard deviations. And I did this, and I got 0.0204. Sorry for these tiny numbers, but that's what's going to go in here with a t star. What will t star be? Let's leave a blank for t star, and this is our standard error plus. Now, how are we going to get t star? How many degrees of freedom? There's n minus 2, which is 25 minus 2. That's 23 degrees of freedom. So we are going to have to look on a curve, the t curve with 23 degrees of freedom, and get this t star for 95% in the middle. Sorry, I didn't draw it very well. It should be out to there. So I want t star. So let's do that together. And so we go to the curve, and t star for 95. So what do you want to do first of all? You want to look at for 23 degrees of freedom. So we're looking down here. Okay? But 95% confidence interval is 2.5 on either tail. So you follow this all the way down to 23, and do you see you get 2.07? Does everybody understand that? Do you understand that? Okay, so let's put that in, then we'll be almost finished. So you could at least do the homework here. So we're going to put that in, and then we'll say 2.07. That's what t star is. All right. And then if you wanted to compute a confidence interval, why don't we start right here next time? Okay? Does that sound good? We'll start right here next time.